Hello everyone, I'm James Goell, Chair of the MIPI Technical Steering Group and a Vice Chair of the Display Working Group. Rick will introduce himself after the end of my first section. Thank you for joining our MIPI DevCon 2021 virtual event. Today I'm excited to talk about the latest developments within the MIPI Automotive SerDes Solutions or MAS specification line. This group of specifications is designed to work together to provide low power, high bandwidth display and camera end-to-end solutions for automotive systems. This presentation provides a high-level overview of MAS, and interested readers will find more technical details in the public links at the end of this section. Many automotive applications are driven by new industry trends described by the acronym CASE: connected, automated, shared, and electrified. Connected automobiles use advanced LTE and 5G networks to increase network bandwidth and drive higher resolution displays. Advanced automation allows new applications more time to use higher resolution and more plentiful connected displays along with connected sensors. Sharing is a natural consequence of automation and provides more opportunities for applications to use end-to-end camera and display with interconnected GPU and ECUs. Electrification requires low power, light, and efficient displays. Traditional automotive applications continue to demand increased resolutions for both displays and camera and frame rates while reducing power consumption and electrical interference tolerance. Let's expand on a particular display from the main cabin example to help illustrate how MAS enables the display to support stricter functional safety goals. In this figure, a low-profile automotive camera sensor with a wide-angle lens replaces the traditional passenger side mirror along with an embedded display. The digital side mirror replacement reduces the driver's blind spot with advanced optics, works at night and in low visibility, poor weather conditions. It also has additional sensor capabilities to detect objects and cars that may not be visible to the driver. In this figure, the automotive ECU has analyzed the sensor data and digitally rendered additional safety icons and warning symbols on the display. In this application, the automotive display has strict safety goals requiring ASIL-D certification based on the appropriate automotive hazard analysis. This level of integrity requires additional pixel information to ensure it can meet the ASIL-D definition defined in ISO 26262. The MAS family of specifications is designed for end-to-end functional safety and, in the future, security. In this diagram, the camera radar on the left, here, uses MAS specifications to capture data and protect it with functional safety and security protocols marked in these icons, all the way from the sensor through the ECU through to the display. And this is all done using the A-PHY SerDes interface through each of the different sections. Here, the ECU image signal and graphics display processors work to generate new pixel output data for the displays. MAS specifications can be used to provide safety and security for these pixels from the display processor through the A-PHY SerDes and finally to the display of the glass here. End-to-end MAS approach is sometimes called glass-to-glass because it works from when the light is captured by the sensor all the way through to when the light leaves the display. Automotive functional safety is standardized in the ISO 26262 series. Among many other references and requirements, these standards define an automotive-specific, risk-based approach for determining automotive safety integrity levels, or ASILs for short. ASILs are used to specify which ISO 26262 requirements apply to avoid unreasonable residual risk as defined by application safety goals. Mass display specifications use the ISO 26262 Part 5 Product Development at the Hardware Level specification as the foundation for display pipeline functional safety. Specifically, informative Annex D, evaluation of the diagnostic coverage, provides detailed guidance on the evaluation of diagnostic coverage required for compliance with single point fault and latent fault metrics, and on evaluation of safety goal violations due to random hardware failures. Annex D provides an analysis of hardware failure modes for display safety engineers to consider when trying to meet their display safety goals. Table D6 defines safety mechanisms and key performance measurement recommendations applicable to mass display interfaces. The mechanism outlined in the bottom 4 rows and outlined in the red box can be combined to provide high, typical, achievable diagnostic coverage. These mechanisms are information redundancy using CRC32 codes, frame counters using unique 16-bit codes, and timeout monitoring implemented using a countdown mechanism. As stated in the last row of the table, a combination of these 3 mechanisms provides high achievable coverage. The MIPI Display Services Extension, or DSE specification, defines a new packet type that implements the safety mechanisms described in Annex D, Table D.6. These service extension packets, or SEPS for short, are calculated during the pixel-to-byte conversion of the DSI2 protocol encoder. The figure illustrates how a SEP header and footer packet is placed at the start and end of each blanking and active line in the video defined by DSI2 long packets. SEP header and footer packets also protect the command and control interface for DSI2 short packets. The MIPI protocol adaptation layer for DSI2 defines the requirements for SEP packets, and its use is mandatory when DSI2 long and short packets are converted to A packets, data framed and sent over A-PHY. This figure illustrates how SEP header and footer packets surround both DSI2 short and long packets. The DSI2 long packet payload and SEP header is used to calculate the CRC32 value located in the SEP footer. These combined packets then form a new payload for an updated DSI2 long packet that may be transferred over A-PHY. The same process is used for the conversion of DSI2 short packets. It is instructive to understand some of the important SEP packet details. The first 32 bits of the SEP packet header, or EPH0, contain the EDT, or extended data type, that defines the SEP payload format. The DSE specification currently supports MIPI DSI2 and MIPI PAL for VISA, EDP and DP SEP payload types. EPH2 contains the SEP 16-bit message counter. It is set to 0 for the first packet delivered in a configured functional safety display frame session and is incremented by the transmitter by 1 for each transmitted SEP packet. The display application may choose to reset the message counter at the start of each line of active video or at another application-specific time in the SEP packet transmission. The key value of the message counter is to uniquely identify SEP packets with a monotonically incrementing value. If the end display sync decodes the SEP message counter and it skips, repeats, or misses the next ordinal value, an error condition must be asserted and appropriate system-level action be taken. That is, an error warning on the display is flashed. Timeout monitoring can also be implemented by tracking the validity of decoded SEP message counter values by the display within a given number of vertical sync signals. The frame rate is known, and thus the number of SEP message counter values between vertical syncs indicates whether the host has stopped sending display data within a given threshold. This is critical for specific safety icons. This block diagram explains the mask display functional safety and, in the future, security system level approach. The top diagram shows a bridge-to-bridge mask solution that is best suited for existing legacy ECUs and displays. The ECU on the left generates source pixel data that is connected to an A-PHY transmitter bridge using a standard MIPI, DSI2, or VESA EDP native interface. This is denoted by the blue arrow. The A-PHY SerDes transmitter uses the MIPI protocol adaptation layer, or PAL specification, to convert this native pixel stream to an A packet protected with functional safety security, or HDC protection. The A-PHY SerDes receives, verifies the A packet's functional safety, security, and HDCP integrity, and then converts the A packets back to native DSI2 or EDP pixels using the same PAL specification. In this example, the FUSA and security are established only between the MIPI A-PHY bridges. In the second diagram, it illustrates a mask display architecture with a fully integrated A-PHY, where the functional safety and security are added right during the generation of the display pixels and maintained all the way through the A-PHY link until the very end when the display decodes the data and sends it to the screen. This is a typical example of the mass end-to-end display solution because this fully integrated A-PHY example does not require an A-PHY SerDes bridge, but this will take time before the market fully adopts this solution. As we will see in the next few slides, it's also possible to achieve mass end-to-end functional safety and security without integration of the A-PHY bridges by using integrated MIPI display services extension specifications into the next generation DSI2 ECU embedded protocol generators. This diagram expands the vertical protocol stack format to provide the low-level details on how the services extension packets, or SEPs, can protect the pixel payload end-to-end from ECU display source to the final display glass. On the left, there are four major blocks: the display source, an A-PHY receiver bridge, an A-PHY transmitter bridge, and a final display sync. The thick black dark arrows indicate the primary physical connections between the C and D-PHY connections, between the source and bridges, and then between the A-PHY transmitters and receivers. On the right side is a detailed payload breakdown for each layer in the stack. The following two slides expand upon the detail for the top and bottom sections. These diagrams are expanded from the top section of the previous detailed display protocol stack. On the left block is an ECU display DSI2 source generator that generates display pixels and sends them down towards an external A-PHY bridge using the native DSI2 over C-PHY or D-PHY. The first block in the ECU pixel frame buffer. It contains the final composited data destined for the display sync. On the far right, you can see the pixel display buffer is scanned in raster order from the top down to generate the display data bytes in green that are used to calculate the display values held in the services extension packet. The SEP enhanced packet header, or EPH, and enhanced packet footer, EPF, contain the CRC and other SEP field data based on the green payload. This new SEP plus data byte information forms the new payload for the traditional DSI2 long packets. It is important to note that command and control information is also protected by SEP header and footer to form a similar payload to DSI2 short packets. These DSI2 packets follow the traditional header and footer structure and are sent through the C or D-PHY as defined in the appropriate MIPI specifications. On the display sync block, the steps are reversed, and each DSI2 and SEP header and footer are verified for correctness. If the display sync detects an error, the mass display family does not specify how the ECU source or display sync should react, but only that the appropriate error handling and reporting must take place. On the left side of this diagram, the block is the DSI2 receiver to A-PHY transmitter, and on the right side block is the A-PHY receiver to DSI2 transmitter. The left bridge receives the DSI2 long and short packets and uses the protocol adaptation layer for DSI2 or PAL specification to convert them into properly formed A packets for transmission over A-PHY. The reverse steps are performed on the right block to reproduce the original DSI2 long and short packets sent over C-PHY or D-PHY. The protocol payload description on the far right illustrates how the DSI2 packet data is recovered and framed into A packets. The details of this are described in the A-PHY specification. These two diagrams translate the previous vertical automotive protocol stackup into a detailed horizontal data pipeline. Legacy automotive ECU display sources produce only native DSI2 or VISA EDP can still leverage mass display specifications to provide functional safety and security, and in the future, security between A-PHY bridges. The first diagram illustrates MIPI legacy display source and sync using DSI2 with either C or D-PHY transmitters. This ECU is connected to an external DSI2 to A-PHY bridge. The legacy ECU has a traditional DSI2 interface without FUSA or security added to the protocol. Once the data is received into the A-PHY bridge, the protocol adaptation layer for DSI2 adds functional safety and, in the future, security using the DSC specification before the pixel data is transmitted across the A-PHY SerDes interface. The second diagram shows a similar arrangement for a legacy VISA transmitter. The protocol adaptation layer, or VISA EDP, adds functional safety and, in the future, security before data is transmitted across the A-PHY. This diagram illustrates mass using new ECUs that have fully integrated A-PHY. These new ECUs with fully integrated mass display specifications can take advantage of the full end-to-end functional safety and, in the future, security of the display services extensions used by the protocol adaptation layers. In both these diagrams, the protocol adaptation layer is fully integrated into the ECU at the start of the pixel protocol encoding pipeline. This ensures that both DSI2 and VISA can include the functional safety and, in the future, security in both the DSI2 and VISA DP native streams. The pixel stream is protected all the way through the A-PHY, through to the final pixel protocol decoder, and directly to the glass. This slide contains a series of useful links to public MIPI documentation to expand upon the mass details discussed in my presentation. I'll now hand it over to Rick to talk about security.
Security within the mass, the guiding principles. There are three guiding principles upon which MIPI security is based. First of all, the PHY, secondly, the protocols, and thirdly, the extent. These are the three guiding principles of the MAS set of protocol suites in total. MIPI security is implemented as extensions to the CSI2 and DSI2 protocols used broadly across many ecosystems. By attaching security to the protocols themselves, this enables the security to achieve an end-to-end extent or reach. You can see in the upper portion of the figure where the bridge-to-bridge and end-to-end data protections are shown. Here we discuss the MAS collection of specifications. You can see the two primary applications, camera and display. Cameras, LiDARs, and radars fall under one category. The displays fall under two categories of specifications, the MIPI DSI2 and the Visa DisplayPort. You can see in the stack that the MIPI security, consisting of both functional safety and security protections within the same layer, is directly attached above the CSI2, DSI2 DisplayPort protocols. On the very bottom is shown the A-PHY data link layer and the physical layer. Security is implemented fundamentally at the protocol level, which enables the end-to-end extent described previously. Some of the high-level system and security requirements are described. Fundamentally, security includes three key elements: data authentication, which establishes a level of trust among the components; message integrity, which ensures that messages have not been modified in transit; and confidentiality, which is achieved through encryption. We refer to data protections in MIPI according to the MIPI 1 to 5 model shown below. There's more on the next page. Security is fundamentally managed by a central controller engaging with each of the other components on a one-to-one fashion. This is not a more peer-to-peer type of model of security. For example, data security may be initiated in the controller number 1 or its bridge number 2 and terminated in number 4 or number 5. Camera security may be initiated in the reverse direction from number 5 or number 4 and terminated in the number 1 controller or its bridge. We'll talk more about the 1 to 5 model next. The 1 to 5 model is shown in a little bit more detail here. Graphically, you can see a display and camera, denoted number 5, connecting through their bridges, number 4, onto the A-PHY network. On the other end of the A-PHY network are the other bridges that are connected to the SoC, number 2 and number 1 respectively. So you can see that there's any number of different variations of these components in a particular system at a given time. In the lower right-hand corner, we can see all 5 of them present. You can see only 2 of them present and in different arrangements. The system requirements we discussed previously, the authentication, integrity, and encryption. Some of the system requirements are fundamentally based on an end-to-end extent, or the ability to secure at the protocol layer. Naturally, security is needed for both display and camera, data plane and control plane. There's a highly flexible operation available. For example, in the display case of a daisy chain topology, where multiple displays are connected in a daisy chain fashion to a controller, some displays may be DSI2, others may be DisplayPort, and the security is uncompromised in an end-to-end fashion. Here we show the MIPI security framework, which we often refer to as the ABC model. So here we have the 1 to 5 model jointly with the ABC model. At the top level, the C level provisions authentication credentials. This is an integrator function. Imagine this as a USB stick pushing down keys into each component. It can also be automated over the air or over Ethernet connection as desired by the integrator. It's currently out of spec in the MIPI set of specifications. MIPI does specify the B level and the A level. B level you can imagine as a software function known as the SSMC, System Security Management Controller. On the bottom, level, A level, this is the execution of the data protection under control of the higher level, B level. Imagine this as hardware that does encryption, it does message integrity, and so forth. It supports 3 different levels of security: A-PHY, CCI in the case of camera, as well as SEPS security for display and camera data planes. MIPI security leverages the DMTF.org specification known as SPDM. DMTF is used across multiple organizations in the industry: PCI-SIG, CXL, NVMe, and most recently MIPI. SPDM is modeled after TLS, which is the security framework used on the World Wide Web. Fundamentally, there are 2 steps. First, there is a handshake to establish authenticated session keys, and then session keys can then be sent to secure the data across the data plane and control plane. Again, SPDM messages are defined generically, but in the MIPI case, these are carried across the DSI, CSI2, as well as CCI or I2C in order to protect each transport individually, as was shown on the previous slide. The MIPI SEP format, this is one of the key elements of MIPI security. Service extensions packet. The SEP format consists of a SEP header and a footer that encapsulate the payload. Payloads include CSI2 and DSI2. You can see in the lower right-hand corner, the native protocols have their native packet headers and native packet footers. These are the regular implementations of CSI2, DSI2 in the market. The SEP header above identifies all the security controls, including HDCP and functional safety. The footer contains the key elements of integrity check value, or MAC, as well as the CRC. The payload here generally consists of a CSI2 packet or a DSI2 packet, and once protected, it can be transmitted immediately. End-to-end application level. So this is a key component of MIPI security. The choice was to model MIPI security after TLS, and it places the MIPI service extensions at the application layer, the source, and the sink. This is essentially as end-to-end as possible, from the pixel source to the pixel sink. In the figures, there are 2 examples on the left showing the transport from application source to application sink over C-PHY, D-PHY. On the right, the same, but carried over the long-range A-PHY. The purple dots illustrate the end-to-end nature, essentially where pixels are created and where pixels are consumed in the application processor. In summary, the MAS specifications provide functional safety solutions today for cameras and displays in the first versions of CSE and DSE. These specs are complete and available to MIPI members. The CSE version 1 and DSE version 1 specs are currently being updated to support security over CSI2, DSI2, as well as the CCI I2C sideband. One of the critical elements of MIPI security is the placement of security in the protocols themselves allows end-to-end data protection with or without intermediate bridges. Again, this allows application layer security like TLS, contrasted to link layer security like MACsec.
Rick, I don't know if you have a couple questions that were addressed to you already, if you want to cover those.
Yeah, I do. One came in, it was, how did MIPI come up with a so-called 1-to-5 model on pages 18 and 19? It seems quite flexible. Does that imply complexity? So good question. We had a good model that we looked at initially from the PCI Express group. In that model, it consists of very similar to what MIPI ended up with. There's a host or a controller. They call it a root complex. And then there's a peripheral or endpoint. And then they have intermediate switches. So in the MIPI context, it was very similar. There's, of course, a controller, and there's a peripheral, which is either a camera or display. MIPI doesn't necessarily call the intermediate components switches. We call them bridges or SerDes bridges. So that kind of formed the topologies. PCI Express also uses DMTF and for security. So that kind of helped us understand, some of the use cases that, that PCI Express uses. So in effect, we had a very good model to think about. And over time, of course, we tailored it to the more specific use cases that MIPI has, which is basically high-speed asymmetrical interfaces, which is very different than than other organizations. So that was yeah. Hopefully that gives some idea of the background.
Great, thanks, Rick. Do we have time for any other questions? I know we're kind of a little bit over here. Rick, do you want to cover anything else?
Yeah, there's one question more security based. It says MAS supports HTTP as well as security. What's the difference? Well, I think the short answer is HTTP, as everyone knows, is really for protecting Hollywood content or premium content. So that's certainly valid for displays. It's not so much relevant for cameras. However, in addition to HTTP, in many cases, you need to support other security. We mentioned a couple of those situations. One of them is supporting mutual authentication, which is in effect establishing a level of trust between, let's say, the controller or the ECU in the car and a component. If somebody swaps in, a component that's not trusted, that is unable to establish kind of trusted connections, that's not going to be of value to a car manufacturer. So HTTP is very uniquely identified for protecting premium content. The other aspects of security are more general than HTTP, things like the authentication and things of that nature. So very different use cases.
Great, thanks. I think we do have time for maybe one more. If I think we had one more come in earlier today. If you want to cover that one.
Right. So the question was, we talked about MIPI display service extensions, the DSE. James also mentioned about it. Is the DSI2 protocol unchanged when using DSI2? Does DSE support the current C-PHY and D-PHY native interfaces? So the answer is yes. There were a couple of figures when you go back. You can see that the DSI2 packet structure is unchanged, and it's essentially tunneled with the SEP headers and footers. And by the way, the DSI2 payload could be very well compressed with the two VISA display compression standards as well. So it also supports that. The C-PHY and D-PHY, of course, are both supported. That's not so much at the DSE layer; it's more at the PAL layer, lower in the stack. So to answer your question briefly, DSI2 is supported directly with or without compression. C-PHY, D-PHY are supported within the lower layer PAL.
Great, thank you. Thanks, Rick. Definitely appreciate you taking the time.
Yep, absolutely. My pleasure. And again, if there are any questions on the topic, would be certainly happy to, take them afterwards.
Yeah, definitely. So please feel free to reach out to us after the event. As we said, all of the presentations will be available on MIPI.org. And with that, I would like to officially close our Asia track for the MIPI DevCon 2021. Thank you all for joining us today. Big thank you to Rick and our other speakers for joining us for this special session. Thanks for demo participants, sponsors, and our committee.